Hello YouTube. In this video I'm going to explore Ulam games and how they demonstrate a rather simple connection between logic and geometry. I'm assuming you have a basic understanding of Wukaschewicz logics, although you could probably follow this video even without that. Here is a simple and probably rather boring game for at least two people. Suppose we have some finite set of numbers. One of the players chooses a number and the other player must find out which number they've chosen by asking a series of questions. So you might have a set of numbers between 1 and 200, and one of the questions might be, is the number between 1 and 100? You find the number that way. A rather boring game, as I said. But let's consider an example game played between Frank and Bob. Our search space, which we will call n, is the numbers 1 to 10, so we're looking for a number in between them. Frank chooses the number 5, which is unknown to Bob, and Bob starts asking questions. Is x an element of 1 to 5? I'm using this capital E here to represent the set theoretical element of sign. So sorry about that, but that's the best I could do with PowerPoint. Couldn't be bothered to look through all the symbols to find it, so we just got a capital E. Anyway, he asks, is x an element of 1 to 5? Frank says yes. Is it an element of 1, 2, 3? Frank says no, and so on. And he can say in the end that x is 5. Now, what is obvious about this is that our search space can be any finite collection of numbers, and we have a simple decision procedure for finding our number. Things get a bit more interesting when we allow the answerer to lie. Now, provided both parties know the number of lies, it turns out that we can also give a decision procedure for these games, and we can provide a geometrical model of this procedure. Essentially, to solve a game with n lies, we need an n plus 2 valued Wukaschewicz logic. So 1 lie means we have a 3 valued Wukaschewicz logic, 2 lies is a 4 valued Wukaschewicz logic, and so on. And how this works will become clear as I explain a game. Right, so firstly I'll describe the case of a game with 1 lie, which needs a 3 valued Wukaschewicz logic, and after that I'll generalize it to any number of lies and any number of valued logics. Right, let's consider this setup of the game. We have a finite set, n, of numbers. The answerer chooses some number x that is unknown to the questioner, and the questioner must find x by a series of questions. The answerer is permitted to lie exactly once, so we'll say L equals 1, the number of lies equals 1, although he doesn't have to lie, but he can if he wants. And that's the basic setup here. Now, throughout the game, we'll be tracking the knowledge states of the questioner. We have the knowledge states KO, K1, K2, and so on, and corresponding to those knowledge states we have the times TO, T1, and so on. At T time TO we have the knowledge state KO, at time T1 we have the knowledge state K1, and so on. And the knowledge states essentially represent what we know about our set of numbers. Now, since we have 1 lie, we need a 3 valued logic, and we can use the values 0, 1/2, and 1. In order to understand how all of this works, it's best to proceed by example. So let's consider a particular game. In our first game, the search space is a set 1, 2, and 3. Our target number x is 1, and we will allow the answerer to give 1 lie. Now, the knowledge state is a vector corresponding to n. So the first knowledge state, KO, is 1, 1, 1, and this corresponds to n, 1, 2, 3. The first number in the knowledge state corresponds to the first number of n, the second number of the knowledge state corresponds to the second number of n, the third number of the knowledge state corresponds to the third number of n. And our goal, remember, is to locate one of these numbers in n. Now, these numbers in the knowledge state will change as we ask our questions, as we learn more about our search space, basically. So the first knowledge state, 1, 1, 1, can be read as a state of total ignorance. We have no preference about which number in n it might be. Any guess would be as good as chance. Right, let's get started with the first question. So we might begin, is x an element of 1, 2? And the answer we get is yes, which just happens to be true. So how do we proceed? Well, the answerer can respond only yes or no. So we have two cases to consider. And I suppose, first of all, let's consider the case we've just observed, where we have the answer yes. Right, so here's what we do. We take our knowledge state, 1, 1, 1, and remember that each entry in here corresponds to a number. So when we have a yes response, the values corresponding to the numbers in the set to which the answer was given stay the same. So in this case, we had a yes response to the set 1, 2. So our first two entries in the knowledge state stay the same, because we had a yes to 1, 2. That means our first two entries in the knowledge state stay the same, so they stay at 1, 1. Now, the values corresponding to any numbers not in that set drop to the next lowest value of our logic. So our search space was 1, 2, 3. The only number not in the set that we asked about is 3. So the third entry in our knowledge state drops to 1/2. Right. Knowledge state KO was 1, 1, 1, and after applying these two rules, we now have K1, which is 1, 1 and a half. And it should be obvious how this corresponds to the search space and to the question that we've asked. We asked, is x either 1 or 2? And the answer has been yes. So we drop the value of 3 because we've been told that it's either 1 or 2. So you can see how that corresponds to the new knowledge state. Well, what about if we get the answer no? Now, this is just the converse of yes. When we have a no response, the values corresponding to the numbers in the set to which the answer was given drop to the next lowest value of our logic, and the values for the numbers not in that set stay the same. So for example, if we'd had a no in response to is x an element of 1, 2, our knowledge state would change from 1, 1, 1 to 1/2, 1. I think that's fairly simple stuff. One thing to note is that since 0 is the lowest value, once we hit 0 we don't drop the value anymore. 0 is as low as we go. Right, let's continue through the game. So we might say is x an element of 1, 3, and here we have our first line. As you can see, it drops like that, and we continue through the game. Now at this point, we have is x an element of 1. Remember, we don't drop the value for 3 since 3 is on 0. And this really makes sense. What 0 tells us is that we know that x is not 3. When we get to 0, we know it's not 3. And really that's kind of obvious, because just look at the responses to the first two questions. We know that one of these responses must be the truth, because we only have one lie to consider. So we have two responses here, one of them must be true. Well, if the first response is true, then our number is not 3, because it's either 1 or 2. And if the second response is true, then our number is not 3, because, as you can see, he responded no to is it 1 or 3. So either way, our target number is not 3. We know it's not 3. We can know that. So it's on 0. We don't need to consider 3 anymore. And the game continues. Now, when the knowledge state contains only one non-zero entry, the game ends. So the game ends here. Our knowledge state has only one non-zero entry. The other entries are 0. That's the end of the game. And these kind of states are called solution states. it should be obvious that the non-zero entry corresponds to the number we're searching for. So remember, our target number was 1, and the corresponding non-zero entry in the knowledge state is the value that corresponds to 1. Now this method will work every time. It's a simple decision procedure for finding the number. So it's a fairly simple method that will work every time. To handle more lies, we need to extend the truth values of our logic. In the case of one lie, we had a 3-valued logic with the values 0, half and 1. And recall what I said earlier, for n lies we need an n plus 2 valued logic. So where we have 2 lies, we need a 4-valued logic, and the values may be represented 0, 1/3, 2/3 and 1. And it's fairly easy to see how this can work. Suppose we have a search space of 3 numbers, 1, 2, 3. Our unknown number is 3, and we have 2 lies. Well, let's look at a sample game. Here's a sample game here, and note that when we get to knowledge state 3, we know that it's not 2 because 2's on 0. Again, as with sort of last time, one of these 3 answers must be true, which rules out the number 2. So there's a simple game there. Interestingly enough, the non-zero element here actually tells you not just what the target number is, but it also tells you how many lies have been told. Because if no lies had been told, we would have ended with 0, 0, 1. If 1 lie had been told, we'd have ended with 0, 0, 2/3. And in this case, of course, 2 lies have been told, so we've ended with 0, 0, 1/3. And this works no matter what the search space or values of our logic. Right. Well, I said that we can provide geometrical models for all of this, and these are really quite natural. Where our search space is the size n, we need an n cube. So where our search space is 2, our knowledge states correspond to the vertices, edges and face of a 2 cube, a square. And since this is the simplest, we'll look at this first. So let's consider a very simple game where our search space is 2, and suppose our unknown number is 1, and of course we're dealing with 1 lie. So suppose this is the game here. We say, is x an element of 1? No. Is it an element of 1? Yes. Is it an element of 2? No. And you can see, very simple game, and we find 1 with 1 lie. Right. Here's a square with the knowledge states labelled on it, and how this works is basically the vertices, as you can see, the vertices correspond to a knowledge state, the edges correspond to a knowledge state, and the face of the square itself also corresponds to a knowledge state. The game begins at vertex 1, 1, and then it moves down the cube, perhaps over the face, until it reaches an edge or a vertex with only 1 non-zero component. Of course, in the case of a search space of only 2, we only have 2 components. So basically we just move over the square until we reach an edge or a vertex with a 0 in it. It's very intuitive. Vertices correspond to states containing only whole numbers. The edges and the face correspond to states containing half. So this game here is very easily modelled. We begin at 1, 1. We move left to 1/2, 1, then down to 1/2, 1/2, and finally down again to 1/2, 0, which is a solution state. So let's consider the case of a search space of 3. For this, we need a 3 cube, or just a conventional cube. And I haven't labelled all of the vertices, edges and faces here, but you should be able to figure out the rest fairly easily. Now again, as you can see, the vertices here represent states containing only whole numbers. The edges represent the states containing 1 fractional component, and the faces represent states containing 2 fractional components. That still leaves us with half, 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 and that's represented by the cube as a whole. So just imagine moving into the center of the cube rather than along the outside of it for the state half, half, half. Well, I think you get the idea. Now, obviously, this does get quite complicated fairly quickly. A search space of just 10, so if we're searching among just 10 numbers, that would require a 10-dimensional hypercube. Obviously, I'm not going to try to draw that. But this is interesting enough, I think. And I mean, I think this is fairly intuitive stuff. Again, we begin here and then just move along our cube around the outside of our cube, perhaps going inside of it until we reach a solution state. The solution states on this would be down this side, down this edge, and along this edge. Just this edge here would be half, 0, 0. This edge here would be 0, half, 0. So you can see that these here are the solution states. Right then, so what we've seen is how to represent one lie with a search space of 2, and this cube here is one lie with a search space of 3. And you can see how to represent expanded search spaces. Well, how do we represent more lies? It's easy enough, and I suspect you may already have some idea of how to do it. Let's consider our search space of 2 again, so we're back to the square. We simply have to partition the square into different portions. So here's the case for 2 lies and 4 valued logic. And it should be fairly obvious how this method can be extended into any number of lies, any number valued logic. So you can see that this is 4 valued logic. We have 0, a third, 2/3, and 1, so that's 4 values. And this represents all of the values that we would assign to this square. Now note that the partition lines, these blue lines here, do not correspond to knowledge states. They're just sort of borders between different knowledge states. They don't themselves represent any knowledge states, and that's why I've put them in blue. So all that corresponds to knowledge states here are the vertices out on the outside outside edges, and the 4 faces in the middle. Right, well, let's see this square at work in a sample game. So let's consider a game where we have a search space of 2, our target number is 1, and we have 2 lies. And here is the sample game just here. Right, well, as you can see, we begin as always at 1, 1, and then we move down to 1 and 2/3. We move down again to 1 and 1/3, and we move across to 2/3, 1/3, across to 1/3, 1/3, and then finally down to the solution state at 1/3, 0. And that's a very clear representation of that game. I note that this provides a very clear visual representation of what I mentioned earlier. The knowledge state we end with tells us how many lies have been told. If we'd ended with either 1, 0 or 0, 1, then there have been no lies. Those two vertices here, 1, 0 and 0, 1, correspond to games in which no lies are told. You can see that in this particular game, as we have the lies, we've moved across to the left there. Right, well, suppose we increase our number of lies to 3, then our square would look like this. Obviously, I'm not going to write in all of those values, but you can see how we can easily fill that in, and we have a square where we have a search space of 2 and 3 lies. So now suppose that we go back to 2 lies, but we increase the search space to 3. Well, in that case, we'd be dealing with a cube, and as before, we partition it. Bear in mind, again, the partition lines do not represent values, and of course I haven't filled in all of them, but you should be able to, if you have a look at that, you should be able to see how that works there. As before, the vertices are all whole numbers, so we have 1, 1, 1 there, moving across 2/3, 1, 1 along that line. This bit here, this line here, would be 1/3, 1, 1. Then we have 0, 1, 1. This face here is 2/3, 1 2/3, and you can see how all of this would go down. We go down to this face here, that would be 2/3, 1 1/3, and then this face, this line here, would be 2/3, 1 0, and you can see how that works. Now, and you can see how that works. And as the number of lies increases, of course, we can keep breaking up our cube into smaller and smaller subcubes. If we had 3 lies, we'd have to break it up even more, and so on. Well, that's it for today. Thanks for watching. Goodbye.